And welcome back. We are here for more networking fundamentals, Microsoft Virtual Academy. We've been tearing through this throughout the modules you've seen so far. We're going to have more for you. This isn't even the end right here. So if you're feeling overwhelmed, well, it's a good thing it's a video. You can pause it, have
take a break.
Yeah, we just got back from a break, so hopefully you're taking breaks adequately. And we can tear right through these with everybody watching.
Oh, Christopher Chapman, Thomas Willingham.
Oh yeah, hi, Christopher. How's it going? This is Thomas.
In case you're just joining us,
Yeah.
if you're just joining us, hey, welcome to the 983366 Networking Fundamentals. Look I'm not even looking at my hand.
It's pretty impressive, actually.
Thomas Willingham, Christopher Chapman, we are your presenters. As I said, if you're coming back, welcome back. If you're new, see what you think. There are other modules that you might want to take a look at.
Yeah. So we're going to jump right into Module 4, Understanding Internet Protocol. And I'm going to, one more time, hand it off to the gentleman to my right, Mr. Thomas Willingham, to kick this off.
Okay, Understanding Internet Protocols. Again, back to our objectives. For our objectives, we're talking about working with IPv4 and working with IPv6. So Internet Protocol version 4 and Internet Protocol version 6. So Internet Protocol version 4, IPv4, is the fourth version of the Internet Protocol, yet it's the first version to be widely deployed. It's the frequently used communications protocol for the Internet. And IP resides on the network layer of the OSI model, 7 layers of the OSI model, application, presentation, session, transport, network, physical, data link, and physical. I almost had it.
There we go.
Almost had it. So 7 layers of the OSI model, 4 layers of the TCP model.
Clearly, as witnessed now, clearly you're going to need all 7 of those layers every day of your IT career. Because we've used them so much that we remember them without any hesitation.
Without fail, without hesitation. So our IP addresses. So we've talked previously about MAC addresses, media access control addresses that work at layer 2. IP addresses are addresses associated with the TCP/IP protocol that uniquely identify devices on the network. They consist of 4 octets, 8 bits, between 0 and 255.
At what layer?
At what layer? The networking layer. And that would be layer 3 of the OSI model.
Awesome.
So examples include 125.5.24.2. So you can kind of read through these, 192, 168, 354. So these are just some examples of some different addresses. In order for an IP address to function, there must be a properly configured IP address and compatible subnet mask. To connect to the internet or any remote network, you'll also need a gateway address and a DNS address. Classful network architecture. So the IPv4 classification system is known as a classful network architecture. It's broken down into 5 sections, class A through E. Class A is your IP range, your first octet, 0 through 127. Your default subnet mask, 255.0.0.0. Let's step back here for a minute. We're talking about network architecture. We're talking about classes and subnet masks and ranges. So we've talked a little bit about subnetting already. And subnetting, the idea behind subnetting is having a network portion and having an ID portion of the device, of the address. So the network portion designates what network is my device on. The host ID designates, well, what's my specific ID number. So 192.168.0, all our devices are on that network. My specific device is .1. So my network ID, 192.168.0, my host ID, .1. The subnet mask is basically what shows what the IP addressing scheme is. So what's the host ID versus, or what's the network ID versus what's the host ID. The subnet mask is basically what differentiates those two. Different classes have different default subnet masks. You can make your own mask. We'll talk about that later. So Class B, IP range, 128 to 191, your default subnet mask. Use the first 2 octets, 255, 255.0.0. Notice the network ID, .net, .host, .host. So the first 2 octets are used for network ID. The second 2 octets are used for host ID. We talk about networks possible and then usable addresses. Notice for usable addresses, it's the number, the bit number minus 2. Why? Well, all zeros is the, let me make sure I get this right, is the unicast address. All ones is the multicast address. Is that correct, Christopher? Did I have that right? Or is that backwards?
I don't know what zeros. You got the all ones is broadcast.
Broadcast, there we go, broadcast.
Multicast is 2, I don't remember, 240? 240.
Okay, so basically you have to strip off the lowest address, all zeros, and the upper address, all ones. The lowest address is now I'm blanking out again, is the broadcast address. The upper one, it represents the network. The 255 represents the network.
So, and when he's talking about zeros and ones, something we cover in a couple of slides is that an IP address is a base 10 number system representation. Numbers we understand, 124, 25, 6. The base 10 representation of a binary number. An IP address is actually binary. From the machine standpoint, it's a binary number, zeros and ones. So when we say all zeros, we mean 0.0.0.0. When we say all ones, we mean 255.255.255.255, because that's the representation of all of those binary digits being 1 versus 0. And we'll get to that. Like I said, in the next couple of slides, we're going to teach you about subnetting, and then you're going to never want to watch one of our videos again.
Subnetting's fun. It's good times. Good times. Loopback testing. So as we've mentioned, not all of the addresses are valid within the range. The range for Class A is 0 to 127. 127, though, is used for what's referred to as a loopback address. And loopback testing allows you to basically ping your own machine. So if you want to basically gain access to your own machine, you would ping 127.0.0.1.
If we want to see a little demo, I got one sitting here waiting.
Oh, hey, Christopher has a demo for us, so why don't we go over to Christopher's machine here, and he can demonstrate.
That right there. So we haven't talked about the ping tool. We're going to talk about that in this course, but it's a way for me to just make sure something exists on the network. In this case, as Thomas mentioned, 127 is a loopback address. It's an address my computer is going to use to check itself. Yep, my computer's functioning correctly. The TCP/IP protocols are working correctly at this point, from what I can tell.
And part of troubleshooting, as you're troubleshooting your system, is you want to troubleshoot, first of all, connections to a FAR system, a server of some kind. If that doesn't work, then you'd want to test intermediary devices, so your switches, your routers. If that doesn't work, then you need to go back and test your own connectivity to make sure that your own TCP/IP stack's working.
Yep.
And using the loopback address is how you do it. Also, if you're doing, say, web development, and you are doing some preliminary testing of a website or a web program, you can use 127.0.0.1 to basically get internet on your own, or I'm sorry, web services on your own machine. So usable addresses. Usable addresses are going to be, as we mentioned, 2 less than the mathematical amount. The all zeros and all ones are taken out. The first and last addresses cannot be used. The 0 for the host address is the entire network. All ones, so 255 for the host address, is the broadcast address. Class D and E's are not used by regular hosts. Class D's for multicasting. Class E was reserved for future use, but has been given away to IPv6, which we're going to talk about in a little bit. And IPv6 is neat stuff, so you should stay tuned.
Yeah. I warned you. I warned you this was coming. So now we get
okay,
to
so really quick, warning, math alert. So we're going to have a little bit of math. We're not going to have a ton, but we're going to have some. So we're used to base 10. Base 10 in the one column, 0 through 9. Then the next field, 0 through 9 again. So ones, tens, hundreds, thousands. That's the system we're used to. Binary, the first field is 0 or 1. The second field is 0 or 1. The third field is 0 or 1. And what these ones represent is the first one represents 1. The second one represents 2. The third one represents, Christopher?
4.
4. So if we have 1, 1, 1, 1, if we have 4 ones, what does that represent?
That's going to give us 15.
15, yes. So it's just a different way or a different method to represent numbers. Binary is typically what computers talk, binary or hex, hexadecimal. We're not going to get into hexadecimal here, but we will talk about binary. So this little conversion chart here that is displayed basically shows, hey, here's the different fields. So we see 1, 2, 4, 8, 16, 32, 64, 128. And then the decimal equivalent of numbers on the right-hand column. So now we're going to go over to Christopher's machine, and he's going to demo using the calculator how these different numbers look.
Yep. So let me clear this while we're getting everything converted over. Now we're going to do some conversion. I've got the slide up behind me so you can actually see the reference we're talking about. And you see this decimal equivalent 224 in this binary representation. We're going to do some checking real quick. We're going to type in 224. We're in decimal. We're just going to switch to binary. Let's take a look and see if the computer and the slide match. And in fact, they do. 0, 0, 0, 0, 0. We've got 5 zeros and 3 ones. Just a moment ago, Thomas asked about what would 4 ones be. Well, let's find that out. We're in binary. Let's type out 4 ones. Oops, not 5. And go back to decimal. 15 is indeed the answer. So this is a great, if you want to use these slides as a calculator, it's very simple. It's got this conversion. You are going to have to go into programmer mode to get the decimal and binary options on here. And you can do these conversions and honestly do as many as it takes. For me, binary was an aha moment. I'd heard about it, I'd read about it, I tried to figure it out, One day it just clicked, it just worked, and I knew how to do it. So do conversions, play around with it, experiment with what numbers you can get. In this case, 253. Think about what that's going to look like. Now in this case, because of the fact we're in the programmer calculator, you're sort of going to get the answer right here ahead of time even before you convert to binary. So what you might want to do is start with the binary, because you can see that, and then convert in your head to the decimal and then check it here. So. And
I don't know about the test nowadays, but back in the day, when I took the test, you actually had to know a bit of binary. You had to be able to convert. Do you have to convert on the test now? Or?
I remember. I just took the MTA a couple of months ago. I don't remember. I don't know. I don't think so. But this is more. So this knowledge, for the sake of the test, like I said, I'm not really sure. You may or may not need it. But for the real world, if you're creating subnets, if you have a need for subnets, you absolutely will need it. It is dry, it is math, it is kind of boring from time to time, but it is absolutely crucial information to have.
Yeah, if you're going to do any type of network architecture, where you're dealing with subnets, you're creating networks, you will have to know subnetting. It's as simple as that.
Yep.
IP conflicts. So we talked a little bit earlier about MAC conflicts, media access control conflicts. There can also be IP address conflicts. So two devices share the same address. There's a Windows error, there's an IP address conflict with another system on the network. Well, how could that happen, Thomas? You might ask. Well, let me tell you. So you might have a system that's currently asleep that has an IP address, and another system comes up online. Let me step back. Let me talk about DHCP very, very quickly. So DHCP, Dynamic Host Configuration Protocol, haha,
nice,
see, fun,
nice.
Again, fun with abbreviations. Dynamic Host Configuration Protocol, what this does is, as a machine boots up, remember this was in a different module, The very nice graphic with the two computers talking to each other, where the one computer was like, "Hey, I need information," and the server was like, "Here's information for you," and the server or the client was like, "I love you, you're the best ever," and the server's like, "I know, I rock." Remember that slide? Okay, well, when this first comes up, it's like, I need an address so I can communicate on the network. And a DHCP server will basically say, well, here's an address for you, and will hand a address out. If a system's asleep and currently has an address associated with it, the DHCP server may not know, and basically say, hey, this address is reusable, give it to somebody else. So when the system that's asleep comes back up, now we have address duplication. And the two, remember what I said about MAC addresses kicking each other off the network? You'll get an error and you'll basically have conflict. Besides DHCP, you can also create a static configuration. So we're used to, as we boot a device up, we automatically get an IP address. There's the ability to statically configure an address and associate a specific address. You could create duplication that way. So there are address conflicts that can occur. You'll need to resolve that. If it does, the addresses will kick each other off the network.
I can give a great example, real-world example of kind of a side story in terms of IP conflicts and keeping track of them. I actually managed a network at one point on a consulting basis. They had a network. They didn't have any IT people. It was about 250 devices. That network did not have a DHCP server. So 250 devices with manually assigned IP addresses. So my method for avoiding IP conflicts was a spreadsheet that someone had printed years before, not even electronic at this point. It was a physical piece of paper, or multiple pieces of paper in this case, that had IP addresses 1 through 255 that we would write in names of devices when we gave them that address. And I would get a call once a week. This went on for about a year that I got a call once a week. Hey, we're adding a new computer. I'd drive over there, take my list, give it an IP, write it down, go back to my office. Just 3 or 4 minutes worth of work. And we build an hour minimum every time. That's how consultants work. So after about a year of doing this, I'd started having conversations with the manager on site about maybe putting in a DHCP server to, one, make life easier because I'm billing them a certain amount of money every time I drive out there every week. And then the conflict, the potential for conflict is amazing. As computers have come off the network that we haven't documented, that they may not tell us about, that as the range fills up and I start reusing back at the beginning, it could be a nightmare. I finally did convince them to spend, I think, about $100 on a piece of software that actually ran on a client that did DNS and DHCP so that we didn't have to manually assign addresses anymore and eliminate the greatly increased potential for IP conflicts. Not a problem you won't have to deal with, especially on a network that size where you don't know where anything is. So even if the computer comes up and says there's an IP conflict with a device on your network, I now have 250 computers over 5 city blocks of, I won't talk about what kind of business it was. A big business, geographically dispersed business, 5 city blocks of space that I would have to go to dozens of buildings to find the device that has that IP to change it or to fix it.
Or it could be a server in a closet. So you may not even walk the floor and see it. It could be a server in a closet.
What servers?
Or it could be maybe a router or a hub.
They had access points. They had switches. They had all sorts of devices. Half of them we probably didn't even have documented at the time. It was potentially a nightmare. So the fact we got them to put in a DHCP server was a huge benefit.
Right, and that goes back to the documentation phase. So ensuring that you have appropriate documentation for your network to just help it to be easier to run. I mean, it should be easy to manage. Public and private addresses. So IPv4 addresses are further classified as either public or private. Public IP addresses are ones that are exposed to the internet. Private IP addresses are hidden from the internet and other networks. So it mentions some private addresses. For Class A, it starts with 10.0.0.0, B 172.16, C 192.168. For most of those with a home network that possibly have a DHCP server running, you may not even know you have a DHCP server running. It might just be part of your switch/router that your internet provider brought to you, and you have DHCP running. We'll show you in a later module how the tools that you can use to check your address information out. Take a look and you'll probably see one of these sets of addresses associated with the devices in your home.
Probably true.
Static and dynamic addresses. So Christopher has talked about the horrors of static addressing. And it's not even necessarily that static addresses are bad, because there's certain devices on your network that you want static addresses for. Your servers. You don't want your servers constantly changing addresses.
Your routers.
And your routers.
They're kind of required.
Correct. So for those devices, you'll have static. So the idea is to minimize the static devices or the static addresses in your environment, and then the rest that come on, request services, possibly come off, they get dynamic IPs.
Absolutely.
And that would be served by a dynamic host configuration protocol server, a DHCP server.
I like that we're using that whole term.
Well,
I like it.
You have the knowledge, you got to use it, right?
That's true.
A PIPA, A-P-I-P-A. So if you've ever booted a device on a network, and, first of all, a PIPA, automatic private IP addressing. Mm-hmm. If you've ever booted a device on the network and were unable to get network connectivity, and you kind of did some troubleshooting and were like, well, I have an IP address, and it's 169.254 blah, zeros, whatever it is. This is a number, so as I said, as a device comes up on the network, with DHCP server here, so you have your DHCP server, your client comes up and says, I need an address, and the server says, I have an address for you, and sends the address, and then remember the huge love fest, I love you for giving me an address, and the server says, that's okay, because you're a great client. So now, if a device comes up and is unable to get to the server, it basically says, well, okay, I asked for a DHCP server or address, and I didn't get one, so I'll just make my own. And then, that's where the 169.254 comes in. I'm going to give myself a 169.254 address. Well, then it can't talk to anybody. So now it has this great address. Woo, I have a great address. Yay, me. But I can't talk to anybody, so then it's sad and lonely.
So what's the advantage of that, though? Why, if all it does is create isolation, why do we have it? Why does it exist?
That's a good question.
What's the advantage to a PIPA? So let's assume you're a small business, or even at home, and maybe for some reason at home you don't have internet. I know the odds are very remote, but it's possible. Small business is a little bit more likely. We've started a business, we have people using computers, we don't have an internet connection, which means we don't have a router to potentially supply DHCP services. And we're business people, we're not computer people, so we don't know what DHCP is or how routers work or that we need any of this stuff. We just bought 10 computers and they came in and we plugged them all in and turned them on and they came on just fine. The advantage to a PIPA is in an environment like that where I don't have a device providing DHCP, those 10 computers are still going to communicate with each other because they're all going to give themselves the same a PIPA network ID. And the host IDs are dynamically generated but don't matter in this case as long as they're unique. And as each of those devices comes up with a PIPA address, it's actually going to send out a little request saying, are there other PIPA devices I need to know so that I'm unique on the network and can now talk to the other devices?
So even if I don't have a DHCP server in my environment, I can still have intercommunication between devices.
If you've got a switch and cabling and you plug those 10 computers on or in and turn them on, they're still going to be able to communicate with each other via PIPA.
Do you know what this tells me? This tells me TCP/IP is swell.
It is.
It takes care of you even if you don't have a DHCP server in your environment. Default gateway and DNS server. Okay, we've talked about the different networks and subnetting. Typically, your device will only speak to devices on its own network. If I need to speak to devices that aren't on my network, that's where a gateway comes in. A gateway gives me the ability to talk to devices on other networks. So basically, I can access my own network just fine, but now I need to access a device on the other network. The minute I see, or the minute my device sees, hey, I'm going to try and talk to a device on another network, now it knows I got to go to my gateway. My gateway will allow me to communicate with devices on my other network.
What kind of device will that typically be?
It could be a server. A server. So we talked about services that a server provide. A gateway could be a service that a server would provide.
What would that service be called in the Windows world?
I thought it was called the gateway service.
Not anymore.
Oh, it's not?
Routing and remote access.
Ha! Routing and remote access, again, you learn something all the time.
So in this case, you're turning a Windows server into a router. This is one of the things I don't want to say I wish it would change. The title default gateway is a misnomer in that it's almost always a router you're pointing to. Whether it's an internet router at home to get to the internet or a router at work to get to other networks, they say default gateway, but it's not a gateway device by the standards of what we've talked about in these modules. So a little quick misnomer to hopefully avoid confusion later when you're going, we don't have any gateways on my network. Well, you do have routers, and that's what a gateway should be.
And basically, this is the default device. So if I'm trying to access another network and it's not on my network, I can say, hey, I'm going to send this to my default gateway, and I know it'll take care of it.
Yep.
DNS. So we've talked about names being associated to IP addresses being associated to MAC addresses. DNS, domain name server, it basically has the ability that this name is associated to this address. So www.microsoft.com is associated to an address, and the DNS server is the one that associates that name to that address for me. So I don't need to know the address of the machine. I just say www.microsoft.com. DNS translates that into the IP address, and then sends me where I need to go.
Absolutely.
We have a demo.
We do indeed.
Christopher, so we're going to talk about IP address properties, default gateway, routing and remote access.
Indeed.
And then the DNS server.
All right, so I'm back on my little demo environment here. This is all set up. It's got an IP address. I actually run the HTTP server in this environment, so it's all there. We're going to jump into our command prompt, and we're going to, I'm actually going to give everybody about 30 seconds to think about what I ran earlier in a previous module to get information about my network adapters addressing information. And while I'm talking, I'll just let them think about it, see if they can remember what it was before I actually type it on the screen. To get that information from a command prompt, you can use ipconfig, and we're going to go over more of this in a future module as well in much greater detail. Now, the downside of this is it doesn't quite give me everything we're looking for. I get an IP address. Awesome, that's my IP address, 10.0.0.39. I get a subnet mask, and I get a default gateway. What am I missing? What else are we trying to find in this information?
DNS.
DNS. I need name servers. Anybody know? I'm wondering if somebody at home knows and is probably screaming at the computer right now trying to get me to hear them, what I can do to get that information out of this tool.
Is there a switch that you could use?
There is indeed. If I use the all switch, I get much more information. And we'll come back up to this same network adapter. I now get the network adapter type. It's physical address. This is the MAC address we've been talking about. I get my IP4 address and subnet mask as I saw before. I also got DHCP information in this screen. Lease obtained, lease expires. This tells me how long I've had and will have the IP address I have from the DHCP server I got it from. And then right down, and also the DHCP server itself. Down here at the bottom, DNS servers, I have 2 configured. That's for various different reasons that I probably won't cover in this course for the sake of depth. And this is all the information I might need to know. And then we'll talk about IP6 later on. For now, we'll just cover the IP4.
Okay, so let's talk about network address translation.
Awesome.
So we talked about IPv4 being 4 octets of numbers, so basically 4 series of 0 to 255. The problem with that being is that's a limited amount of addresses. I mean, sure, that's billions of addresses for about 4.3 billion addresses. The problem being is as we start to add devices, this is global. Everybody, and now the proliferation of devices, nowadays it's not uncommon for a single person to have 3, 4, even more devices that access the internet. So your phone, nowadays people have watches, Fitbits, tablets, computers, laptops. All of these need their own addresses. 1 billion globally can get used up pretty fast.
It can.
So basically what they came up with is network address translation, or NAT. Basically what this is a method for translating addresses from one network onto another. So as we mentioned earlier, the 192.168, if you're in a small office, home office, or you're on a home network, you'll probably see that address. How is it all these different environments can share the same address when we've said that people need, or devices need, unique IDs to connect to the internet? Well, that's where network address translation comes in. With network address translation, it translates addresses from one network, 192.168.0.1, to another network, typically internet-facing address. So now you or your company can be assigned one physical address on the outside. So internet-facing, you have one physical address. Inside, you can use 192.168 and have a whole bunch of devices internally. The NAT device allows that translation.
For some more geek knowledge, I've got on my screen right now, if we can get it up here, there's the comparison. The numbers of available addresses in IPv4 and IPv6. So there's a little bit of a difference in IPv6 for how many are available. So NAT, very required or very necessary in the days of IPv4, which we're still in. Not so much in IPv6.
And that's one of the benefits of IPv6 is more addresses, is getting away from that scarcity of addressing. And you have to remember, TCP/IP, when they first created, they were just starting to talk about networking, interconnectivity of devices. It kind of went back to that 256 megs of hard drive. Who would ever fill that up? Nobody will ever fill up 256 megs hard drives. Well, then video, Word documents, blah, 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 and then stuff started to fill up. So IPv4, the same thing. Initially, there were a certain amount of addresses, devices interconnected, but now with the proliferation of devices, there just needs to be more addresses.
Well, and here is just for, again, for some reason I like doing this particular demo when I'm in classes. I just added a number to this. That's the number of IPv6 addresses per person alive on Earth right now.
Oh, there we go.
So yeah, so for some good gauges of, you could have approximately, I don't even know how many numbers that is, but that's how many devices any person could have and still get a unique IP address for every single one of them. Yeah, a few.
A couple. So that will cover my 5 devices.
Go grab another phone. I'm just saying, let's take advantage.
What kind of phone might somebody grab?
Any kind of smartphone, preferably
Windows phone.
Preferably
grab
Windows 8.
Phone. They're nice.
Windows
They're
8,
nice.
Surface. Grab one of those.
And connect to the internet.
We will give you IP addresses for days.
Yeah. We're happy to.
We are.
We're happy to.
Indeed.
Okay, so network address translation, if you look at the slide here, as we said, it's the process of giving addresses or modifying addresses from one system to another. And you basically see we have some devices here, 10, 11. We have a hub or possibly a switch to allow those to intercommunicate with each other. But then we have a network address translation device here that translates our internal network to internet facing. And again, your device that you get from your internet provider probably has NAT translation in it, or network address translation in it.
If it doesn't, it probably doesn't connect you to the internet. So
Probably.
odds are
Probably.
that technology is there and working.
So there's a network address translation. So in this graphic here, you see connection type, DHCP client, quality of service engine, active, cable status, connected, network status established, connection uptime, your MAC address, your IP address, your subnet mask. default gateway, DNS, so primary and secondary DNS. Now notice, so our address is for the WAN, wide area network. The LAN is your local area network. So between your local area network and your wide area network, your network address translation is occurring. So to create these networks, we use a process called subnetting, and this is where that math comes in. So it's a subdivision of your local or your logical IP network. By default, all computers are on one subnet, and you need to use the subnet mask to configure this a bit. By modifying the default subnet mask, you can store your subnet into your network onto smaller networks. So you look, your type, your class A, class B, class C, see the decimal equivalents and the binary equivalents.
Yeah.
So our subnet IDs, here's some different subnet IDs, the binary equivalent, the host IP range in binary, and the host IP in decimal. I'll just leave this up. There's nothing really, you can kind of review this a little bit. You might want to pause on this and kind of read it if you're a little bit more interested. Subnets, so your net ID, subnet ID, your host ID, your mask, number of usable subnets, and number of hosts per subnet.
So this one demonstrates one of the concepts behind subnetting. We've talked a lot about the default subnets in the prior slides, 255.255.255.0, that first one. The option or the process of subnetting beyond that, in this slide, you see how the mask changes. It doesn't end in 0. We've looked at 255.0.0.0, 255.255.0.0. These don't end in 0. And what subnet masking allows us to do is allows us to take a range we've been given and break it into smaller networks without adding more networks or adding more routers. Let's say we don't have routers. We can't create these distinct networks using hardware. It's another software method to do it. We use a subnet mask to sort of borrow bits from what would be the host ID portion of your IP address and lend them to the network portion, network ID portion. In this case, this table demonstrates or shows us how the bits break down in terms of that borrowing. The net ID, the subnet ID, and the host ID, they're giving us those the second and third columns numbers of bits. In the top example,
so the host ID, we're using all 3 octets.
Yep.
The net ID, that we're using all 3 octets for the net ID. The subnet ID column shows you how much of the host ID, how much of that binary from the top we're going to borrow. And then the host ID shows how many bits we have left over to create hosts.
The actual host, yep. So this is a topic that it's very difficult to cover, especially via video. Usually I'm on a whiteboard doing multiple different translations, creating subnet IDs and breaking them into the number of networks and the number of hosts. This topic is one we may delve into in a subsequent video. There may be other resources to look at. Subnetting is a very important topic. It's one everyone should learn. There are, I hate to say this because I didn't use any of these when I learned. I'm not even sure they were out yet. There are calculators out there to help you determine and build subnets and subnet masks if you need them. I would say don't use them. I'm a purist. Although I sound like, I used a slide rule to do multiplication. I used calculators. My parents used slide rules. I did this on paper. Kids nowadays, kills me to say that, will have calculators to do subnetting. So
I think we're kind of done with subnetting. I think
so. It's a tough one to try and cover in a video, honestly.
Oh, it really is.
It's difficult.
Well, and there's that whole Q&A thing. That's really kind of difficult. So we're giving you some really good basic information. Don't be afraid to go and search and look up additional information on these topics. If you see a topic and you're like, I still don't quite get it, feel free to search for additional information on it.
Bing is chock full of content.
Bing it. IPv6. So we talked about IPv4, fourth generation. Now we have IPv6, the new generation of IP addressing for the internet. Solves some of the limitations of IPv4, such as scarcity addresses and security. They're represented by 8 groups of 4 hexadecimal digits. It's not backwards compatible with IPv4. It's a 128-bit system versus IPv4 was a 32-bit system. And this kind of gives you some information Christopher already gave you. IPv4, about 4.3 billion. IPv6, 340 undecillion. That's that number, undecillion.
Undecillion.
So our address types, there's a unicast address, an anycast address, and a multicast address. A unicast address is a packet designed for a specific network interface. So this is a packet for a single network interface for a single device. There are 2 types of unicast addresses: global unicast address, which are routable and displayed directly to the internet, and link local addresses, automatically configured addresses to communicate with devices on the same link. So these aren't globally routed.
So link local is very similar to your PIPA.
Okay.
It's sort of the IPv6 equivalent. I say sort of loosely. There's IPv6 is like subnetting. We're not going to get to go into nearly the depth.
No. There's an anycast address. This identifies multiple interfaces, but the packet is sent to the closest one per routing. Multicast address, the packet is delivered to multiple devices and multiple hosts. The address components, they're broken down into 3 parts. The site prefix, the first 3 groups of numbers define the network. The subnet ID is basically similar to a subnet mask. And the interface ID is the host portion. So demonstrated here on the slide, an IPv6 address. Notice how large it is. And then the table here breaks down the site prefix, which is 48 bits, the subnet ID, which is 16 bits, and the interface ID, which is 64 bits. And now we have a demo of IPv6.
So in this demo, not terribly involved. It's really just a matter of we're going to bring up this same tool we looked at earlier and have a look at IPv6 in action. I have IPv6 on this network. Now, I'm not using any sort of IPv6 DHCP or any sort of, which, again, I wish we could dig into this more. I wish we had more hours in the day to go into IPv6. Now it differs from IPv4. DHCP potentially may not be used on a network using IPv6. That's all I'm going to say. Look up some more information. Maybe we'll do an IPv6 deep dive video one of these days. This is actually what's called a link local address. This is an automatically generated IPv6 address on my computer. And you can tell that by the prefix FE80. They're very similar to a PIPA as 169.254. Link local generated addresses are FE80 or FEC0. I believe there are 2 different ranges that could be assigned.
Well, and I would have the watchers notice here, the video watchers notice here that there's a link local IPv6 address, and yet there's still an IPv4 address.
Absolutely.
This is referred to as a dual IP stack. So both of those stacks are running simultaneously.
Absolutely, and that allows me to communicate with IP4 devices on my local network as well as IP6 devices on my local network or out on the internet. There are a number of sites, public sites now working on IPv6 that are running and using IPv6. So the goal at this point for a lot of providers, internet providers especially, is to make this transition seamless. At home, you'll never even know you've been changed to IPv6. In corporate networks, it's going to be different. It is an effort. It is an actual project that has to be undertaken to implement it correctly and make sure that there is no interruption of service.
Well, and part of the issue is all your intermediary devices, switches, hubs, routers, gateways, they all have to understand this new referencing ID, this new addressing system, and so there's cost involved. There's upgrade, whether it be hardware or software. There are upgrade costs involved to get this working. Or training, yeah, exactly. More training. And remember, how much are these MVA courses, Christopher?
Let's see. These cost nothing.
Absolutely nothing. Again, a hug of knowledge for you.
Indeed.
Okay, so I talked about the dual IP stack. That's the next slide here. So I'm going to blow past this. We talked about it while Christopher was doing his demo. IPv4 mapped addresses. So basically what this is the ability to map IPv4 to IPv6.
Directly in this case.
Correct. Correct. So if you look at the last bullet, notice we have the first 80 bits are set to 0, and that's designated, if you're looking at the last bullet here, by the dual colon sign. So that means the first 80 bits are set to 0. The next 16 are set to 1, shown as FFF. And the last 32 bits are populated by the IPv4. So there's that 10.254.254.1 address that we're familiar with. So this is a way to encapsulate an IPv4 address into an IPv6 address.
Absolutely.
There's also IPv4 to IPv6 tunneling. So an IPv6 packet can be encapsulated inside an IPv4 datagram. It talks about for a Microsoft operating system done with the Teredo adapter, virtual adapter, or pseudo interface. Oh my, my mind went blank.
It happens. It's been a day.
Not a physical network adapter, and then it gives an example, the F80::, which I think we just saw F80 somewhere, didn't we, Christopher?
We did indeed. That's a link local address right there.
Okay.
So yeah, IPv4 to IPv6 tunneling is very handy for implementing IPv6, but not fully. I want clients to get IPv6 addresses. I may want servers to get IPv6 addresses. Let's say that my routers and switches can't handle IPv6 yet. Well, I can implement that technology on those servers and clients, wrap those addresses in IPv4, and then route them through those routers and those switches that will recognize them, and then the server and client on the other end will unwrap them and use the IPv6 addresses.
So we could use this as a method of migration.
Yep, absolutely.
For IPv4 to IPv6.
Yep, and there are a number of these technologies available, so more research for people doing IPv6 implementations.
Okay. We're at the summary already.
We are again.
It seems to me like we're blowing through this content, and now we're just at the summary again.
We need more like transitional slides so we can tell it's coming, more than just, oh, hey, you're done.
Yeah, I feel abrupt. I feel like we're going somewhere, and all of a sudden we're here. And, it's a little jolting.
Well, yeah, but that gets people to watch the next one. It gets you on edge.
Hopefully.
Oh, there's more. Oh, they can't stop now. I got to go to the next video.
Yeah, cliffhanger.
That's what we're trying to do.
So, summary, be able to categorize IPv4 addresses using classifications such as A, B, and C. We've talked about default gateway and DNS server, what they are, and how to configure them. We've talked about defining advanced TCP concepts such as NAT, subnetting, and how to create network subnets. We've talked about the basics of IPv6 and a little bit about how to configure IPv6. And we've talked about the IPv6 dual stack and tunneling technologies.
Yep.
Christopher, additional resources and next steps.
Yep. Once again, we get to talk about what to do next. After this, we've got the MTA book, Microsoft Technology Associate Networking Fundamentals from Microsoft Office Academic course. We've got our instructor-led courses in case you, again, want to get more hands-on, want to use these tunneling technologies in a lab environment, want to implement an IPv6 infrastructure, want to see how the Teredo interface works, way to do that. And then the exam and certification that we're hopefully preparing you for right now, Exam 98-336, Networking Fundamentals.
We're at the end. There's so much more I want to tell people.
There's so much more to be told.
I don't want the video to end.
You can stay if you want to.
Well, I feel really bad. We have so much more to tell people, and this is just over.
I'll let you keep talking. I'm going to go ahead and slide out this way right off camera.
Well, no, I mean they're done with this one. But,
they are for now.
But there's just so you need to come back.
The beauty for us, we're going to make lots more of these for you to come back and watch more of.
So come back.